If you're a power engineer, you need to know per unit analysis. Let me start with a question. How many of you can solve this simple circuit for current? Probably most of you, right? It's simple Ohm's law. What about this circuit? Not so easy, right? If you're naive, you might give the same answer as the previous circuit, but this isn't correct. The impedance seen by the generator is no longer 1 ohm. It's being changed by the presence of the transformer and its turn ratio. The transformer is actually changing the impedance seen by the generator. It actually changes by the square of the turns ratio, which kind of makes sense because let's say we have a step-up transformer of 10 to 1. The voltage goes up by 10 and the current simultaneously goes down by 10. That's a change in impedance of 100. That's the square of the turns ratio of 10 to 1. This is why the impedance seen by the generator differs from 1 ohm by a factor of 100. What about this circuit? Now we have two transformers. What impedance does the generator see? What is the current in each loop? Things start to get complicated because the impedance seen by the source is affected by both transformers. Solving this kind of circuit with standard circuit theory is messy and not intuitive. Unfortunately, our power systems are full of transformers. Solving this kind of system on a grid scale is possible with today's computers, but in the past, a trick was devised to convert the system to something easier to solve. It does this by removing the transformers and normalizing each section to account for the change in impedance. So our circuit, which starts like this, becomes something like this. And we can solve this much easier using basic circuit theory. This method is called per unit analysis, and even though we now have computers, it's still the industry standard method of analyzing and describing power systems. Per unit analysis is used to both simplify the calculation of power system quantities and also make the interpretation of these quantities more meaningful, as we shall see later. First, and before we get into the details of the method, let's make sure we understand the high-level strategy. The principal underlying mechanism by which per unit analysis works is by removing the transformers, by normalizing the circuit quantities, impedance, voltage, current, so the circuit can be solved using conventional circuit theory. Then, when we have our so-called per unit quantities, so current, voltage, etc., we can convert back to real quantities using the same conversion factors. Essentially, what per unit analysis does recognizes the fact that the transformers change the impedance in a predictable way. So we can work out the factor by which each transformer changes the impedances in the system and apply this factor. If we do this correctly, the effect of the transformer, i.e. the way that it changes the impedance with respect to the generator, is taken care of, but we're left with a circuit that is far easier to solve. So let's take a look at an example system. This system has a 1000 volt generator with a 1 ohm resistance. This is connected through a 1 to 10 step-up transformer to another resistor of 1 ohm. Now, I've already simulated this circuit using MATLAB Simulink, so I already know what the currents are. But let's see if we can use per unit analysis to arrive at the same answer. I'll go through the process step by step. Don't worry at this stage if you don't understand it straight away. I will be coming back to what each step is doing a bit later. and we'll also do other examples later on, because there are some nuances and some extra information that we need to understand before we can say we fully understand per unit analysis. Let's take a look. Step one of per unit analysis is to split the system into zones. You do this by drawing an imaginary line right through the center of each transformer. You can see here that since we only have one transformer, we have two zones. A power system might have hundreds or thousands of these zones. Now, splitting into zones is necessary because when we normalize the impedances with the conversion factor, or what we'll eventually start calling base quantities, we shall see that they are different depending on which zone you are in. This is true for base voltage, base current, and base impedance. Now, the one system quantity not dependent on zone is base apparent power, S-base. This is a common quantity that applies universally throughout the whole system. And when you think about it, this does kind of make sense, because whether you're at high voltage or low voltage, the power is the same because the current scales the other way. Now, it's up to us what we choose as S-base. As long as it's consistent across the system, we can, in theory, choose anything we want for S-base. However, it is good practice to choose an S-base which matches as closely as possible the apparent power base of your equipment. This is due to a couple of reasons. Firstly, if the transformer has an impedance, and in these first examples we're assuming that they do not, i.e. they just step up and down the voltage and current without introducing any of its own impedance into the system, but if they did, choosing an S-base that matches the transformer S-base simplifies the process of converting this to per unit. And in a later example, we'll see exactly why this is the case. Secondly, if we choose base quantities that match our actual system, we are more likely to end up with per unit quantities which are meaningful, in the sense that 1 per unit corresponds to normal operation throughout the system. This is really important because in the power industry, it is common to discuss power system quantities in terms of their per unit equivalents. The next step is to choose the base voltages for each zone. Again, we can choose anything for this, but there are two important considerations. First, and for the same reasons we choose a sensible S-base, we also have a responsibility to choose V-base in each zone, which is meaningful. For example, if our rated voltage is 1000 volts, we should aim to choose a V-base of 1000 volts for that zone. This means under normal operating conditions, we should have a voltage of 1 per unit. The second major consideration is to remember that our V-base should follow the transformer ratio throughout the system. So in this example, if we choose V-base is equal to 1000 volts in zone 1, we must then choose V-base is equal to 10,000 volts in zone 2, because we have a 10-to-1 step-up transformer. This is absolutely necessary for per unit analysis to work. Next, we can calculate Z-base and I-base in each zone. Bear in mind that this first example is a single phase system, and the equations for a three-phase system do differ slightly, but it's only a square root of 3 here or there, so don't worry about that yet. We'll come to that a bit later. So the definition of Z-base is V-base squared divided by S-base. And the definition of I-base in a single phase system is S-base divided by V-base. So we can use these equations to work out Z-base and I-base in each zone. And they will be different in each zone because V-base is different in each zone. Now we have all the base quantities describing our system. These act as the conversion factors, so we can go from the circuit with transformers, which is difficult for us to calculate with standard circuit theory, to a circuit without transformers. And this circuit is much easier to work with. We know that our per unit equivalent circuit will look something like this. It will have a per unit voltage and the two converted impedances. Remember, we have a different conversion factor in each zone for impedance. The idea now is to solve this circuit and calculate the per unit current. Note that the per unit current is actually the same everywhere in our per unit system. But look at the conversion factors that we've used. We have an I base which differs by zone, so although the per unit current is the same right the way through our circuit in the per unit equivalent circuit, when we convert back to actual values, the conversion factors correct for the impact of the transformer. For example, we know that the current on the secondary here must be 10 times lower than the primary because it's a 10-to-1 step-up transformer. So if the voltage goes up by 10, the current must go down by 10. And any system that we use must respect this. So if you look at the base currents, you will see that this 10-to-1 ratio is actually there. This is a clue as to how per unit analysis actually works. So to go from actual to per unit values, we need to divide the actual quantities in our system, voltage and impedance, by the base quantities. This will give us the so-called per unit quantities that make up our per unit equivalent circuit. For the voltage, we chose 1000 volts in zone 1, and our source is conveniently 1000 volts. So actual divided by base is 1000 divided by 1000, so it comes out as 1 per unit. The impedance in zone 1 is actually 1 ohm, and the base is also 1 ohm. So the per unit impedance is 1 divided by 1, which is 1 per unit. The impedance in zone 2 is actually 1 ohm, but the base impedance in that zone is 100 ohms. So the per unit is 1 divided by 100, which is 0.01 per unit. So now we have a total per unit impedance of 1.01 per unit and a source of 1 per unit. So now we can just use basic Ohm's law, 1 divided by 1.01, to give us a per unit current of 0.9901. Now, to convert back to actual current, we need to multiply by the conversion factor for current in each zone, so the base current. In zone 1, we need to multiply by the base current in zone 1, which is 1000 amps. And in zone 2, we need to multiply by 100 amps. This gives us 990.1 amps in zone 1 and 99.01 amps in zone 2. Now, if we want to do a quick sanity check here, we know that the current in zone 2 should be 10 times lower than the current in zone 1. That's the case here, so that's a good sign that we're on the right track. And also this matches the simulated value that we showed earlier on. We can make the following conclusions based on this first simple example. Per unit has allowed us to solve the circuit using basic circuit theory. Now, in the power industry, this method has been so useful that it remains the standard way to describe per unit quantities like voltage, current, and impedance. For example, in our simple system, is it more meaningful to say that the voltage is 1000 volts in zone 1 or 1 per unit? Which one is more meaningful? If we choose the latter, any engineer, even those unfamiliar with that particular power system, can be reasonably confident that the system is operating at normal rated conditions. This is one of the reasons per unit is still used today, despite the fact that we now have computers that can solve these circuits very quickly. This is a slightly more complicated example because we have two transformers and therefore three zones. But the method is exactly the same. As long as we follow through each step, we should get the correct answer. So first, we choose S base, then we choose the V base in each zone, making sure that we follow the transformer winding ratio and also thinking about a sensible value. In this case, we have a 5 kV source, so we might as well choose 5 kV in zone 1, because that will give us 1 per unit in that zone. The other two V bases follow from that initial choice. Then we calculate the Z base and I base for each zone, and then we start to build up our per unit equivalent circuit. So Z per unit is equal to Z actual divided by Z base for each zone. Doesn't matter that we have a complex impedance this time, the procedure is exactly the same. Then we solve for per unit current using simple Ohm's law, and now we go from I per unit to I actual by multiplying by I base in each zone. That's it. Now, up to this point, we've assumed that the transformers have no impedance, so they do not appear in the per unit equivalent circuit, and the transformer simply steps up or steps down the voltage and current. However, real transformers do have an impedance, and we need to be able to handle this in per unit analysis. The impedance of a transformer is dominated by the leakage reactance. This is the flux that does not link between the primary and the secondary. As you might expect, this looks like an inductance in the per unit equivalent circuit. But how do we know what value this should be? Well, normally transformers have their impedance expressed as a percentage on their nameplate. I mean, this seems a bit weird because impedance is normally expressed in ohms. However, the percentage impedance makes complete sense in per unit analysis. Let's see how. Let's say we have a transformer impedance of 3%. Now, the first thing to realize is this only makes sense relative to its base values. For example, you would always say something like the transformer impedance is 3% on a base voltage of, for example, 11 to 33 kV and 50 MVA. So it only makes sense relative to those base values. And if you look at a transformer nameplate, you will see the transformer impedance in percent, but you'll also see the voltage ratings and also the apparent power rating associated with that impedance. Well, this is one of the good things about this system. If our per unit analysis system base matches the transformer base values, okay, so let's say we have this transformer within our system and our system voltage bases are 11 kV and 33 kV either side of the transformer, and our system base is 50 MVA. Now, if the transformer impedance is 3%, we can put this straight into our per unit equivalent circuit as J 0.03. Okay, so in a way, per unit has been designed around transformers, and this is a really nice shortcut, but it only works if our system bases match the transformer nameplate base values. So to demonstrate what we do to resolve the case of transformer impedance, I'm going to adapt our previous example. We're still single phase here. We'll move on to three-phase systems a bit later, but here you can see we have some new information. So the transformer on the left-hand side has its rated values given to us So it's rated at 5 kV on the primary side and 200 kV on the secondary side. And it has an impedance of 3% on a base of 10 MVA. The transformer on the right-hand side has a voltage rating of 200 kV to 20 kV and has an impedance of 5%, also on a base of 10 MVA. And the first thing you should take notice of here is that our transformer nameplate information matches our system bases being used for per unit analysis. This is extremely convenient because both transformers can be put straight into our per unit equivalent circuit as J.03 and J.05. And this would represent the leakage reactance of those transformers in our system. And here you can see that we just need to slot the transformers into our per unit equivalent circuit. The 3% transformer becomes J.03 and the 5% transformer becomes J.05. But this is only because we have the convenient case of the transformer nameplate information matching our system base. What happens if they don't match? So in this circuit, you'll note that our transformer nameplate information gives us an impedance that is relative to a different base voltage and base apparent power. So unlike in the previous case where everything matched, we cannot simply put the impedances of these transformers straight into our circuit. But we do have a trick up our sleeve. There's a handy conversion formula which converts the impedance value to a different base. In this case, we wish to convert to new bases that match our system bases. So we simply plug the values in and we get a new percentage impedance. This is now appropriate for our per unit equivalent circuit. Now, so far we've only looked at single-phase systems. For the case of three-phase systems, the procedure is much the same, but there are some conventions that we need to be mindful of. Now, in single-phase systems, there's only one possible voltage and one possible current. But in a three-phase system, we have, obviously three conductors, and we have a choice of taking either the phase voltage and current or the line voltage and current. The convention in per unit analysis is to take the line-to-line voltage, and the power is always defined as total three-phase power. You can see that we now have a three-phase system represented as a one-line diagram. We have a three-phase generator with an internal resistance of 3 ohms, and it operates at 415 volts. Then we have a star-to-star connected three-phase transformer with a rated voltage of 415 volts on the primary side to 11 kV on the secondary side, on a base of 500 kVA with an impedance of 4%. Then we have a transmission line with impedance 1 plus J 0.314, which connects to our second transformer, which is a step down 11 kV to 415 volt transformer, also with an impedance of 4%. Then we have a three-phase load of 0.1 ohms. Our task now is to use per unit analysis to obtain the current in this system. The procedure is much the same as with single phase per unit analysis. First, we draw a line through the center of each transformer, and this will split our system into 3 zones. Then we specify our base apparent power. Now, this is where we need to take a step back and think about how we can make our lives easier, because if we choose the same system base as the transformer nameplate, this means we don't need to use the conversion formula, and that 4% for both transformers will automatically translate to J.04 in our equivalent per unit circuit. If this is not the case, and sometimes it's unavoidable, you can't really avoid having mismatched bases, we just use the conversion formula which we introduced a while back. So we choose a base apparent power, in this case of 500 kVA, so it matches the transformers. Next, the base voltages. Well, we'd be silly here not to choose 415 volts in zone 1 because that matches the operational rated voltage of the generator, and it also matches the rating, the voltage rating of the transformer. Next, we calculate the base impedances for each zone. So again, we just do V squared divided by S base in each zone. Then we calculate the base currents. So here is where something differs compared to single phase. Note the presence of the √3 in this formula. That wasn't there in single phase. This is just something to be mindful of. The transformers are easy, so the J.04 per unit goes straight into the per unit equivalent circuit. And that's basically it. We have our per unit equivalent circuit. We can solve this for current, for per unit current. Then we can multiply by the base current in each zone to get back to actual current. And that's it, it's done. So there we go, that's per unit analysis. We started off with single phase systems. We had a look at how we deal with transformers. Then we moved on to 3-phase systems. And I think I'll leave it there. Now, if there are any questions or if there's anything else you would like me to cover, or if I've made any mistakes, please let me know in the comments. And finally, thank you very much for watching.